Okay, so I guess the question that was asked was basically sort of a reaction to a question that was in the assignments. I'd given you a wave function which went somewhat like this and asked, is this a, or what is the potential for which this is an eigenfunction? Remember, this is not just a wave function. What I said was this is an energy eigenfunction. Now, some of you wrote back quite correctly that this x cannot be the position variable simply because it would make absolutely no sense to put a dimensional quantity on an exponent, right? You all know that an exponent in an exponential has to be dimensionless, right? So this x cannot be the x really, the position variable. It should be q, the one which we used for the harmonic oscillator, for example. Rather, it should be some dimensionless thing which stands for position. So if you wanted x to be the standard position variable in ordinary units, you could have said something like to the minus alpha x to the 4, where alpha, of course, would have a dimension of inverse fourth power of length, so that the overall exponent is dimensionless. Okay. However, let me also tell you that very often we do keep on using units in such a way that the relevant quantities become dimensionless, and we often do it without giving a warning that we are doing it. So I do admit that this should not really be construed. If I wrote e to the minus x to the 4, those of you who told me that this cannot be correct because you cannot have a dimensional quantity up here, you were right, except that very often we will be using dimensionless x's simply by choosing some relevant length parameter in your problem. Some parameter or combination of parameters with the dimensions of length in your problem, and then you will just go ahead from there. And so we will often do this without warning, so that you would often see statements like the Hamiltonian for the harmonic oscillator would be p squared by 2 plus x squared by 2. Which of course makes absolutely no sense in standard units because p and x are entirely different dimensions, and neither of them have squared dimensions which are equal to the energy, right? So, because that is the case, p squared by 2 plus x squared by 2 cannot be the Hamiltonian for the simple harmonic oscillator, or indeed for any system if we were using conventional p and conventional x, and we were measuring energy in conventional units. However, we use this all the time, and when we are using this, the basic idea is we are not using x, which is a position. We are using a dimensionless counterpart of that. Even the Hamiltonian, whose eigenvalues of the energy are really being measured in some standard units of energy, which automatically, in this case, the obvious thing to do would be to use h cross omega, or maybe half h cross omega as the units for energy. Okay, so that's done all the time. Okay, so this is just a warning that we will often switch to dimensionless variables, and it should be clear from the context whether we mean ordinary position variables or dimensionless position variables. Okay, so that while that criticism is correct, I would just point out that we will often do things like this, and so you should not really be too fazed by expressions like this. Now, having said that, let's come back to the original question. The question was, given that this is a wave function, does that tell me what the potential is? I deliberately misquoted the question right now, because given a wave function, can you tell me what the potential is? The answer is of course not. The wave function is simply dependent on what your current state of the system is, right? And just because the potential is a given here, that doesn't tell you that you can control your current state of the system to be only certain things and not others. The wave function, which describes the state of the system at a particular instant of time, has absolutely nothing to do with the potential that describes the system. The potential will govern how the system evolves in time. Okay. Now, the reason why I'm stressing this point, although I'm pretty sure many of you know this, it's still important to be stressed enough that we spend so much of our time calculating energy eigenfunctions that we tend to forget that energy eigenfunctions are really not the only possible wave functions. In fact, frankly, the energy eigenfunctions are important in quantum mechanics, not because they tell you the energy, but because they give you a way of figuring out how the system will evolve in time. If you start with an arbitrary wave system in an arbitrary state, that is some arbitrary wave function, you can expand that in terms of energy eigenfunctions. And since you know how energy eigenfunctions evolve in time, that tells you how an arbitrary state will evolve in time. So energy eigenfunctions really play a sort of helping role here. But unfortunately, most of elementary quantum mechanics courses, a large part of an elementary quantum mechanics course goes into solving the Schrodinger independent Schrodinger equation, finding the energy eigenvalues and so on. So much so, it's actually important to do that. I'm not saying it's not important. All I'm saying is it sort of tends to give people a wrong impression as to what is really important and what is not that important. Energy eigenfunctions are important, but they're not the only thing possible. But having said that, let's come back to what the question really should have been. And in fact, that's exactly, I hope, what the question was in the assignment set. This psi is an energy eigenfunction. Then find out the potential. And the question is, can you always do that? Given the potential, that is, can you do that uniquely at least? Is the potential unique from this? Well, almost. And the answer to that is actually, if not unique, it's actually essentially unique. So what does that mean? It simply means this. You know that this is the Schrodinger equation in one dimension, right? So what does this tell you? This tells you that V minus E, just by rewriting this, will be psi double prime by psi h cross square by twice m. Okay? So all you really need to do is take the second derivative of your wave function and divide it by the wave function and multiply this by this h cross square by twice m factor, or maybe even nothing if you're using dimensionless variables, but at least make sure of what you're using first. H cross square by twice m psi double prime by psi will give you the potential energy minus E. Okay? Two important points here. First of all, the normalization does not matter. You don't have to bother trying to calculate what the normalization factor is. This wave function as given is obviously unnormalized, but it doesn't matter because you're going to calculate the ratio of psi double prime by psi. And in that ratio, of course, this will definitely cancel out. Okay? The normalization constant, whatever that is. Now, does this tell you what the potential is? Yeah, because if you're given psi, this quantity h cross square by twice m psi double prime by psi can be calculated, and to which, of course, you are adding this E, the energy eigenvalue. Now, obviously, what you might very well say is that we cannot find out the potential energy uniquely from here because there's an additional E, which I don't know. I've just told you that there's the energy eigenfunction. I've not told you what the energy eigenvalue is. So I've not told you what the value of E is. Okay? But is that a valid criticism? Okay, what do you think? And the fact that V of x comes out in this form, that is, it comes out as something which you can calculate given psi, plus a constant energy E, which you don't know. Is it okay to say that I found out potential energy, or would you really say that this potential energy is not unique at all? Yeah. So what's your answer to that? Yeah, I'm waiting. I hope I'm still there.
This potential energy is basically a difference at the end of the day, and we more or less have the function. I think it should be unique because at the end of the day, it is the difference that matters, not the actual value.
Difference meaning difference of what?
The potential energy between two different things.
Different change in potential energy when exchanges, right? Yeah, even from very first time when we define potential energy in classical mechanics, it's really the difference in potential energy which makes physical sense. An overall constant shift does not change the physics at all. And the fact that this E leaves the Vx undetermined is actually perfectly understandable. The zero of which point you take the zero of your potential energy to be is entirely in your hands. So you can always shift your zero. In fact, you can even say, okay, let me shift my potential energy zero in such a way that the energy eigenvalue for this particular wave function turns out to be zero. I can always do that. I can just simply drop this term. That will make no physical difference to the potential energy which describes the system. You will still be describing the same system. Okay? So the answer to, given the energy eigenfunction, can you find out the potential energy? The answer is yes. Is it unique? Essential. Not exactly. Is undetermined up to a constant, but that constant can be set to any value you want, including zero. And that's just a choice for the zero of your potential energy. Okay? Anything else? So why can't we choose? Okay, anything else? This why can't we choose? Couldn't read that. Why can't we choose arbitrary phase for orthogonal eigenfunctions, spherical harmonics? Why is the constant shortly phase important? The answer is it's not. It's important if you want to compare different results which you will see in textbooks. That's really why it's important. Okay. Now let me make one thing very clear. You all know that if you use the lowering operator L minus, you will go from the wave function corresponding to Lm to Lm minus 1, right? Now, of course, what happens when you apply L minus on, let's say, suppose you have a wave function corresponding to L and M, that will be some radial wave function times some spherical harmonic, which describes the angular part. This, of course, was the topic of your last two lectures. And suppose I apply L minus on this. L minus, the operator, all the angular momentum operators are completely independent of R. They only act on theta and phi. And there's a very good reason for that. L plus, L minus, Lx, Ly, Lz, all that they do is that they describe how wave functions change when you rotate your coordinate system. And when you rotate your coordinate system, it's only theta and phi which change. R doesn't. So anything which describes rotations will simply not describe anything. Will simply not affect the R coordinate. The R coordinate simply doesn't change under rotations. So L minus, of course, goes and really acts on the y Lm theta phi. And as you all know, what does this really do? It lowers the m value. So it gives you y L m minus 1 theta phi, unless, of course, you're already at minus L, m equal to minus L, in which case L minus will give you 0. And there will be a constant in front. Now, this constant you can figure out by using the standard angular momentum algebra techniques, which you have already done. In fact, you may have used this notation, Lm minus 1, with some constant here, C minus, and you have used the angular momentum algebra to find out C minus mod square. All that is perfectly okay. You can do that. But you get C minus mod square from there. You do not get C minus, right? So you still have a choice of phase here. You can choose whatever phase you want, as long as you do it consistently. You cannot do, what you cannot do is you cannot choose a phase now and then say, okay, when I am going to apply L plus, I will again make another choice. That you can't do, because the moment you have chosen what L minus YLM theta phi is, you are actually choosing exactly which of these infinitely many wave functions which differ from each other by a phase factor, are you calling YLM minus 1. You had a choice until you made a fixed phase choice. Once you have made a fixed phase choice, that thing is done. Okay, Abir has asked, how do we know? Abir has gone back to the previous question and asked, how do we know the ratio of eigenfunction and its second derivative will give similar functional form for other eigenfunctions or in determining the potential? Great question, except that it's really not a question. What he is asking is something like this. I have several energy eigenfunctions for the same potential. I am calculating psi1 double prime by psi1, psi2 double prime by psi2, psi3 double prime by psi3, and so on. Okay. And what Abir is worried about is this. If I calculate psi1 double prime by psi1, I get some dependence on x for the potential energy. Of course, there's an h cross square by 2 some factor, but let's just forget about that for the time being. And then I take psi2 double prime and psi2 and do psi2 double prime by psi2. What guarantees that we will get the same function? Of course, we won't. We will get a difference, and the difference will be the energy difference between E1 and E2, right? But apart from that, how are we so sure that we are going to get the same ratio? Apart from this constant difference, which just tells you that the energies are different. The answer is, if you don't get that, that means you have not found the right eigenfunctions. As simple as that. For a given potential, there is a fixed set of eigenfunctions. Whether you have been able to find them or not is a different issue. For a given potential, under some conditions which we are not going to bother going into, you will always find a fixed set of energy eigenfunctions. Okay? And the reason why they are energy eigenfunctions is that they satisfy this all-important relation. So if you were to take psi1 double prime by psi1, get a function, and use psi2 double prime by psi2, get a different function. When I say different, I mean differing by more than just a constant. Then the only thing you can really say is that either anybody who told you that there are energy eigenfunctions belonging to the same potential is wrong, or they give you two different energy eigenfunctions for two different systems. So two different potentials. End of story. Okay, let me also warn you at this stage that when you say you have solved a potential, it's not whether you have found out a particular energy eigenfunction for that. When you say you have solved the Schrodinger equation for a given potential, what you are supposed to do is find out all the energy eigenfunctions and energy eigenvalues. Okay, that may sound like a tall order, but in principle, that's what you are supposed to do. Okay, and so let me just point out this this particular thing that we did. Let's just say it is a minus x to the 4, and let's put h cross square by twice m equal to 1. I'm just using those units. So x is dimensionless here. This is a psi prime, of course, is minus 4x cube to the minus x to the 4. Psi double prime will be 16x to the 6 by differentiating this, minus 12x square to the minus x to the 4. So my potential energy, which describes the system which has this as an energy eigenfunction, is going to be, apart from overall constants, simply this. A potential which starts off like an inverted parabola. So because of the minus x squared term, when x is very close to 0, of course, x squared is going to dominate over x plus x, right? Smaller powers dominate when you're close to x equal to 0. So x squared dominates. And then when you go further away, x becomes large. The large positive x plus x contribution, remember x plus x is positive no matter whether x is negative or positive, is going to take over, and you are going to go up like this. So this is going to be a double well-like potential, symmetric about the x-axis and about the y-axis and so on. Okay. Given this potential, have we been able to solve it? The answer is no. All we have done is found one energy eigenfunction. Of course, we didn't even do that. Somebody told us, okay, this is the energy eigenfunction. Can you find the potential? So what we are solving here is what is called an inverse problem, which is actually very, very important in many practical situations, because in many practical situations, you may have some measurements from which you want to infer what the system is. So this value, this potential that you've got, okay, has one exactly known energy eigenfunction, e to the minus x to the 4. Does it have more? Of course it has more. It has infinitely many more actually, energy eigenfunctions. Do you know what they are? At this stage, the answer is no. Can we find out what they are? The answer is of course yes. However, let me also warn you that there are no exact solutions known for any of the higher energy levels. You can find them out numerically, you can find them out with great degree of accuracy, but exact solutions, that's something you don't have. Okay. For this particular potential, 16x to the 6 minus 12x square, and precisely for this very special ratio between the two coefficients, you know one and only one energy eigenvalue and eigenfunction precisely. Okay. All the others you have to find out either numerically or via some approximation method. Okay. Now there are situations where you have a potential energy for which say the lowest two energy eigenvalues are known exactly. All others have to be found out using numerical methods. That's very possible. Or 3 or 4 or 5. And of course, you must realize, because of the question which Abhi raised, having only one energy eigenfunction known exactly, that's sort of trivial. Give me any function which satisfies the boundedness conditions, so that, and the normalizability conditions, I can give you a potential that will do the job for that. But to give me two such energy eigenfunctions, of course, cannot be a matter of accident, right? Because you have to ensure that psi2 double prime by psi2 and psi1 double prime by psi1 differs only by a constant, nothing else. Or if you have more than two, that makes it even less likely to happen by just random choice. So these kind of systems, okay, let me just give you the name for these. These are called quasi, depending on whether you want American or English. Quasi exactly solvable potentials. And techniques for generating quasi exactly solvable potentials are still a matter of active research. We know quite a lot about them, but at least for people who want to dabble in the structure of quantum mechanics and find out nice mathematical results about it, this is still a very active source of problems. One exactly known eigenfunction, absolutely no problem. 20 exactly known eigenfunctions, or even 2, that takes some doing. Now, of course, we have this great system, the harmonic oscillator, for which we have infinitely many exactly known energy eigenfunctions. But that's kind of system. The system for which we know all the energy eigenfunctions and eigenvalues exactly and analytically, that is very, very rare. Okay. And at this stage, let me also ask you one thing. I know this is an energy eigenfunction. If somebody asked you, is this the lowest energy, is this the one corresponding to the lowest energy, what would your response be? Yes? How would you justify or criticize this statement that this energy eigenfunction corresponds to the lowest energy?
So I don't think we can do that, right? We'll just have to add a different constant to the potential and say that this is the starting.
No. I'm not talking about lowest can be any value, but once you have chosen your potential, let's say the potential I've used, this is the potential, for which of course the energy for this state has to be 0, right? I've just chosen the additional constant which comes from the energy to be 0, okay? But I'm asking, how do we know this is the lowest? How do we know that there can't be anything lower? Isn't it possible that the same system might have some other energy eigenfunction corresponding to an energy which is negative, or which is below whatever value I've given this one? Gurpahul has already given me the answer. The answer depends on a theorem that we discussed in one of those preliminary lectures. This particular wave function essentially looks like this, right? Okay, it looks even sharper than this is rather wide. It actually doesn't really look like this so much. It looks more like this. Drops off more sharply, stays flatter than e to the minus alpha x square close to x equal to 0, but drops off more sharply as x increases. But the important thing is, it has no nodes except at minus infinity and plus infinity. An exponential does not vanish somewhere for a finite value of x. Okay? Since this is nodeless, this has to be the lowest energy eigenfunction. You cannot have any other energy eigenfunction which has a smaller energy. Why? Because of the oscillation theorem, which tells you that if you have two eigenfunctions belonging to two different energies, the eigenfunction corresponding to the higher of the two energies must go through a 0 in between two nodes of the other eigenfunctions. Since this does not go through a 0 anywhere in between on the real line, this has to be the ground state energy. Okay, so in this case, I'm sure that all other energy eigenfunctions, I may not know what their values are, but I know that they are all above this one in energy. Okay. On the other hand, if somebody gave you a problem like this, somebody told you this is the wave function for some potential, of course not this one, some other potential. You can of course find out the potential, right? Yeah. Again, you just divide psi double prime by psi and throw in whatever additional constants that you want, h cross square by 2s and etc. Of course, for that you will need a dimensional parameter sitting on here and so on. But having done that, you get a potential for which this is an exact energy eigenfunction. Is this the ground state? The answer is no. You can easily show that the function here will go to 0 in between. So this happens to be an excited state for that particular potential. Can you find the ground state for that potential? Almost certainly no. Okay, can you find the ground state? The answer is of course yes. But can you find it exactly analytically? The answer is almost certainly no. Okay, but I'm saying almost certainly simply because since I did not, the chances of my having cooked up a quasi-exactly solvable problem just by that is very, very remote. Okay. So the chance that I hit upon something which is quasi-exactly solvable so that I know this energy eigenfunction exactly, I also can find out some other energy eigenfunction exactly, is very, very low. The chance that I've done this by accident. So almost certainly this is the only energy eigenfunction you can be sure of. All the others you can calculate to very high degree of accuracy. Okay. And for practical purposes, that's all you will really need. But this will definitely not be the ground state, this particular wave function. Okay. So any further questions? Rahul, can you show us the derivation of the Legendre polynomial generating function? I will not share. show the derivation, but I will repeat exactly what I said. The concerns that you have raised here are actually pretty legitimate concerns. You have PL, which is 1 by 2 to the L factorial dl dxl, PL of x square minus 1 to the L. So this tells me that if you have a function which is x square minus 1 to the L, its Lth derivative is given here. But the Lth derivative of a function can be written down in terms of the Cauchy integral formula. Okay. And then what you have to worry about is this. Can you sum up x square minus 1 to the L by L factorial from L running from 0 to infinity by x minus something? Can you do that? The answer is you can. You should be able to figure it out. Okay. Convergence, is that an issue? Of course it is. But remember, there's an L factorial in the denominator here. In the Harmonic polynomial case, there was an L factorial in the numerator as well. Or basically, you actually use the L by L factorial in the generating function. Here you don't. Here you have PLX t to the L summed over. So you have to be very, very worried about the convergence issues here. In this case, convergence will be an issue. But you should be able to figure out. And since by the way, let me give you a very broad and rather, wrong hint as to how to proceed here. If you simply cannot figure out any other way, use the fact that you already know the answer. Back calculation is always bad, but if it helps you teach something about a problem where you can't make headway otherwise, but you can back calculate, by all means back calculate, try to figure out exactly why you were facing problems earlier. Are we making any assumptions about its convergence without stating explicitly? Of course, yes. In fact, this should really tell you anyway that there is an issue here. You have a square root in the denominator, right? Yeah, so convergence was also an issue for the Harmonic polynomials. For example, we could not have chosen the contour arbitrarily close to Z0. Of course, you're right. Convergence is always an issue. In fact, the point is maybe I wasn't very explicit when I stated that. I should have actually perhaps explicitly stated that in the lecture itself. I used the residue theorem. So for those of you who remember that lecture, fine. If you don't, please take a look at that again. When I derived the generating function for the Harmonic polynomials from the Roderick's formula using the Cauchy integral theorem, I used first of all, I changed the sum, this particular sum that we had, this HLX to the L by L factorial. Using the Cauchy integral formula, I changed this into some kind of contour integral. And then I use Cauchy residue theorem. However, what you have to be careful about is that the Cauchy integral theorem only works to give you I actually use the Cauchy integral theorem to write down the derivative which is there in the Roderick's formula in terms of a contour integral, then did the sum. Then I use Cauchy residue theorem to simply evaluate what that contour integral is. However, what you have to make sure is that the contour actually contains the pole that you are getting. So if you, as Sharon is pointing out, if you took a contour which is very close to Z0, a very small circle around Z0, it will happen that my pole will actually end up being outside that contour and the contour integral will vanish. Okay. Now that actually works both ways. That actually tells you that there is a limit to the convergence that you have of the series. So convergence issues are important. So If you've already seen that lecture and understood this, I would urge you to revisit that and try to understand it in the light of how big does the contour have to be. The one good thing about that particular function was that the numerator was an entire function. It was just an exponential which had no poles anywhere in your complex plane. So you could choose your contour to have as large a radius as you wanted, in which case this issue did not really bother us too much. However, for other situations that may not be true, so you have to be very careful. And thanks for pointing that out. I should have actually mentioned that in the lecture itself. Okay, and now waiting for further questions. But did this statement that I made and the question that was raised, did this make sense to everybody? So if nobody is saying anything, I can assume that either they're completely lost or this makes perfect sense. By the way, let me point out that when we worked with the Harmonic polynomial case, ultimately we evaluated the sum of a GP, right? But it was an infinite GP. So this infinite series, what is the sum for this? Is it A by 1 minus R? Yes or no? Only if mod R is less than 2. I'm not sure where you got the 2 from. It's only if mod R is less than 1. Yeah. So the sum of this series is of course not A by 1 minus R for all R. If R is more than 1, this obviously diverges, right? So there we did a sum, which was we summed up an infinite series just by using the A by 1 minus R formula. But when we did that, we had already assumed that this series is a convergent series. And for that, actually tells you how big a contour, how small a contour you can take actually for this to work. So all I'm saying is the choice of your contour and this convergence issue, they're not independent issues. They're connected to each other in the derivation itself. So if you have not seen that yet, of course you should. But more importantly, if you have seen that and not worried about this issue, I would urge you to take a look at that again and now think it over very carefully. In this particular case, as I said, I can make the contour arbitrarily big because of a function which is sitting in the numerator that has no poles anywhere. So there's no chance that I'm going to include any of one of its poles inadvertently. So in this case, it was not a big problem. But in some other cases, it will be. So you have to be very careful about these issues. Okay, since nobody is nobody really asking any other question? If you want to ask a question and finding it too difficult to type fast, you can always say, I have a question first, and then type out. Or unmute and say. Okay, if not, let me begin our course formally today. Remember, all the lectures that we had were preliminary lectures. We have still not finished them. The radial equation has to be solved at least for some problems. So maybe by tonight or by tomorrow morning, you will get the next video, which handles the radial equation. For some very simple central potentials, we will start with one of the simplest problems, the spherical potential well. In the first lecture, and then it will be too much to fit in everything in one lecture. So spherical potential well will be the next lecture. And after that, in the lecture after that, we will talk essentially of two systems, the hydrogen atom and the three-dimensional harmonic oscillator. So in two more lectures, we will finish the preliminary lecture part of this course. Okay. So that will be coming, one will be coming today or early tomorrow morning, the next one by the weekend.